She will talk about non-parametric estimation of McKean-Vlasov SDE via deconvolution. Please, the floor is yours.
Thank you very much. And thank you for the invitation. I'm very happy to give this talk. This is going to be a talk about, I don't know exactly where to put you guys, not here, maybe here. The, the talk is about this paper with Denis, Vitote, Mark, and Shiwi, about indeed polynomial rates via deconvolution for interacting particle systems. So what are we going to do today? First of all, I want to introduce the model. So I will give an introduction about interacting particle system, and I will explain how to connect the particle to the interacting particle indeed, to the independent ones that are indeed the McKean-Vlasov stochastic differential equation. And I will talk about what's called the propagation of chaos, which is a very fancy name used by physics, because physics, well, the physicians, they do stuff in a very fancy way often. And I will explain in detail what is the propagation of chaos, but then I would like to apply it in order to estimate what I will call the interaction function. And we'll see that it's going to be a bit messy because in order to estimate the interaction function, there will be several steps. And the last one will involve a convolution problem. That's where the name come from, the name of this talk, I mean. And that will be the most involving part, because in order to solve the convolution problem, we will have to study it Fourier transform and actually also Laplace transform of the density associated to the process. So this was just the plan of the talk. Of course, now it's too soon and things will be more clear later. And I propose indeed to start directly by showing the model. Okay, so this is the most important slide in one sense because it explains in detail what we want to do. Here we consider an interacting particle system. I believe you can also see my hand, right? My pointer moving. And great. And well, what we are going to consider are capital N, different stochastic differential equations, where there is some interaction. So these stochastic differential equations are not independent, but they're not so far away from being independent. Why? Because the driving Brownian motions here, these BI, are all independent. So I will refer to each of these stochastic differential equation as a particle. And here, what I'm saying is that all the driving Brownian motions are independent, but still the particles are not independent. Why? Because inside the drift part, we have two different parts. We have a confinement potential, where we have the dependence again only on the I particles, but then we have also the interaction potential, which is this WU, where we have the dependence in all the other particles as well. So the different particles are interacting because we have dependence, but inside the drift, while the driving Brownian motion are independent. And this is the model that we consider that is in particular, easier on a general, with respect to a general differential equation, in the sense that here the diffusion coefficient is just 1. So we really want to consider this particular model because we will see that already this one will be quite challenging. Why that? Because we want to estimate in particular the interaction potential. And in order to do that, one very important tool will be the propagation of chaos. So the fact that we can move from this interacting particle system to the independent ones that I'm going to introduce in 1 second. Just a small thing about the notation before going on. You can see that here I didn't call the confinement potential and interaction potential just here as V and WU, but I already took the derivative. Why that? Because later on I will have to work with invariant density and we will see like V and WU appearing. So it was just practical to write here the system already with the derivatives, but it's just a choice. It's not a big deal, okay? So what's the goal here? We want to, I move you again, and this time, you'll go, let's say here. No, not a good choice here. Okay. Okay, I'll stop seeing you. I will see only one of you each time. It's life. Gerardo, you won. So, so what's the goal? As said before, we want to estimate the interaction function, this WU, but starting from what? Well, we assume that we can see all the particles, but only at capital time t, which is the deadline. So we start at the deadline, but then we consider the asymptotic regime where both the number of particles, capital N, and the time horizon go to infinity. So actually, we are going to have an increasing number of observations given by the fact that both the number of particles and the time are going to infinity. And here we see already that as the time is going to infinity, well, the uniformity in time will be needed in all the estimations we are going to provide. Okay, and the goal is to estimate WU. Stop me in case you have questions, don't hesitate. So this is the framework, and as I said already before, a very important tool in this context is to be able to move from the interacting particle system to the independent one. But you see already that I wrote here only one stochastic differential equation, which is this one, and it's not really so far away from the stochastic differential equation I wrote before, but still it's quite different. First of all, why one? Well, because I can take just capital N copies of this one, and I will create in this way the system of independent particles, because as they are independent, well, there's no need of writing already capital N of them. It's enough to take the same one N capital times, of course, with, again, N independent Brownian motions. And here, the difference is that there is no longer an interaction among the different particles that we are creating. Why that? Because inside this equation, there is no dependence on any other particle. And indeed, a nice trick is to rewrite the interacting particle system that we saw before in this way. That is exactly the same stuff that I wrote before, but instead of writing explicitly the other particles, I wrote directly the equation of the particle I as a function of the empirical measure. And that is nice. Why? Well, because it's easier to see how similar the solution of the stochastic differential equation given by the McKean-Vlasov and the interacting particle system are, in the sense that really the equation is the same, but basically in one case you have the empirical measure, and in the other you have really the law of the process you are considering. Okay. And we're going to see later on how we can get one from the other. And well, I said already that this is going to be the limit for capital N going to infinity, so having an increasing number of particles. But it's possible also to to ask ourselves, like, how fast is this convergence happening, and which kind of convergence do we have? We will answer to all these kind of questions, but before going on, I think that we need a bit of motivation. Like, okay, I introduced the interacting particle system and the limiting independent one, but why do we want to work on this? Well, it's nice to give a bit of motivation, and to do so, in this case, it's easy, the fact that we have a lot of different application of the interacting particle system. And this is nice. It's nice because at the beginning, when the interactive particle system have been introduced, they were used by McKean just in the context of statistical physics. Interesting. But the problem was that there were no data available. And things changed later on when people understood that there were a lot of different applications for the interactive particle system on which we actually have data. And so it makes sense to do statistics using this model, because now you have like concrete data that the statistician can indeed analyze. Which kind of data? Well, a lot of them. A first application that is nice to discuss is in mathematical biology, and it's the fact that a lot of society of animals behave as system of interacting particles. And in particular, I don't know why, but it's possible to find a lot of study about fireflies. And it has been proved that they really move as really following a system of interacting particles, like a lot of applied studies on that. Then the second application, which is nice, is in social science. And in particular, it's nice the fact that interacting particle systems have a lot of application in opinion dynamics. And it has been useful, especially after, COVID, after 2020, because this model has been used also to understand like reaction of people to vaccine. Of course, I don't mean like physical reaction, but how was the reaction in the opinion? Like the fact that if you talk with someone and that someone tells you something, tells you his opinion about vaccine, that may change your opinion as well, and so on. So application in the opinion dynamics, and then of course there are the more classical application in finance, main field games, where you have a lot of players, and kinetic interacting particle system in the sense that you have like a stochastic differential equation in 2 dimensions, where you also have like a degenerate one. But of course, this is just to say that there are a lot of application that changes it all. Why? Because starting from all this application, then there are a lot of works in statistical inference appearing. Indeed, it's nice the fact that if we consider just probabilistic tools, interactive particle systems have been discovered the first time by McKean in the 60s. And then starting from the 60s, there are a lot of papers about probabilistic tools for interacting particle system. But about statistical inference, the discussion is a bit different in the sense that if you look here at some of the paper that I wrote here just to give an intuition, with the exception of the early work of Casonga, all the others are quite recent. Why that? Well, because as I was saying before, when statisticians understood that interacting particle system had a lot of application, they started also saying, then we do have data. That's nice. Would be nice to actually be able to give some statistical guarantee about the estimators that we are proposing. Okay. And I started here giving some references about parametric statistical inference. But as I said before, we want to estimate the interaction function. And we are going to see that we will need several steps in order to do that. The main step will be a non-parametric one. So I wrote already the part about literature in non-parametric parametric estimation, and here I give some references about non-parametric estimation. In general, it's not like there's really a lot because it's a very recent topic. So I feel like there was a lot of space until not long time ago. Now it starts condensated, but still it's a very recent topic, and there are still a lot of things to be done. And among all the literature that I wrote here, the most interesting one, the most similar to what I have in mind, is this paper by Denis Vitote and Mark Belomessini, Pilipskite, and Podolsky, where the framework is basically the same. They consider the same interacting particle system I proposed before, and the goal is really similar in the sense they do want to estimate the interaction function, but they obtain an estimator that converges to indeed the interaction function at a rate that is logarithmic, so slowly. And the question is, well, is it possible to do better? Even more than that, I don't know how familiar you are with the convolution problem, but in classical deconvolution problem, if one assumes that a density has polynomial tails, well, the Fourier transform actually, then it's possible to obtain logarithmic rate for the estimation of such density. But if one assumes to have polynomial tails, logarithmic rate. If you assume to have exponential tails, then it's possible to obtain polynomial rate of convergence. And here this is, well, this is different, of course, because it's not like there's only a deconvolution problem and we are not asking anything about the tails of the density. We are already working with the actual interaction function. So we are going to see that there will be several steps in order to arrive till the end, in order to arrive to the estimation of the interaction function. But here the question is, you can do whatever you want. You can add all the assumptions you want. Please give me polynomial rates. Propose me an estimator for the interaction function and show me that the convergence rate is polynomial. Also, it would be nice if that is also optimal, but let's not ask too much so far. So far, let's ask just to have polynomial rates, some polynomial rates. Is it possible to do that? Well, yes, otherwise I wouldn't be here giving this talk, so this is a bit of a spoiler, but it will be quite a path to arrive till there. So there are some stuff that we need, and some of them are really probabilistic properties that we need to prove. So we start by giving some assumption, and of course I don't want to go too much into details, but on the other side I want to give you the key points. And here the key point is that we are going to work with Fourier transform and Laplace transform of density associated to our stochastic differential equation. So it will be important to understand the decay of such transforms. And in order to do so, it will be important to break the continuity of our function. Indeed, we'll see that if you get, well, maybe if you are familiar with complex analysis, you already know that a bit, but the decay of a Fourier transform of a function is very much connected to the smoothness of the function itself. And that is what is behind our two assumptions A1 and A2. Indeed, we are saying that the confinement potential is something that is known, because our goal here, remember, is just to estimate the interaction function. And in this confinement potential, we take two different possibilities. In the first one, V tilde is equal to 0, meaning we are taking the confinement potential that is infinitely smooth. It is C infinity. While in the second case, we break the smoothness in the sense that it's continuous, yes, with bounded derivatives, yes, but only up this integer m. We have a function that is Cm, capital M, no more. And we will see later on how this A2 condition will help us getting some information about the decay of the Fourier transform we are going to work with. We keep the two of them as we really want to see the differences between the case that is C infinity and the case that is Cm for a particular m. Okay, this is like the key point, the key message that I want you to understand from this slide about the confinement potential and about the interaction function that is actually the unknown, the function that we would like to estimate. The thing that I want you to remark is that just that the condition we're putting are a bit different compared to the classical one in this kind of paper, like more from a probabilistic point of view, in the sense that generally one just asks really uniform convexity of WU. We are here asking something that is a bit less but we are going to recover anyway the same condition, just working a bit more. We'll see later on that we have to prove the propagation of chaos that is uniform in time, an extension of it, actually. And this condition is ad hoc in order to be able to obtain the uniform propagation of chaos in this context. So, with this assumption, we're already ready to give some probabilistic result on the invariant density. First of all, we know that the process does admit an invariant density, which is already nice, it's already something. And the first result is to say, okay, even though this V is not just square, okay, it's square plus maybe nothing, or maybe something else, but anyway, under our condition, it's possible to show that the invariant density is upper and lower bounded by something that it's not so far away from being just a Gaussian, let's say. Okay, so we have some information about the invariant density in this context, and this is going to be crucial later on, because we are going to, again, I'm giving spoiler, but we are going to consider the Fourier transform of this quantity. And, well, if you have a Gaussian, and you take the Fourier transform of a Gaussian, that is, again, a Gaussian. So if it is exactly exponential of minus x squared, and you take the transform, then you get again the exponential of basically minus x squared. Why is that a problem? Well, because we are going to put it at denominator. So we are going to see something that explodes, okay? And this will be our main problem later on. We are going to have a deconvolution problem that will make us put the Fourier transform of this invariant density at denominator. And starting from there, we will have some problems. Are there any questions?
Yeah, I have a question about the pi.
Yes.
Yeah, what you're giving about the density is some kind of, well, it's an equation. So how do you check that this solution has a unique, this equation has a unique solution? Because
Okay. Well, it was nice the fact that, well, here I'm going to the following slide, but actually the nice thing is that we didn't have to check anything. We just use a paper from Villani and some other co-authors saying us that the invariant law exists and it's unique under our conditions. That was not a problem, actually.
Okay, thank you.
Thank you. But it's this paper by Villani, Carrillo, and McKean. But thank you. It's a very good point, actually. It's nice the fact that, well, there are already a lot of probabilistic tools, because from a probabilistic point of view, the problem was already interesting and has been considered as interesting for the last, I don't know, let's say 60 years. So people worked already a lot on this kind of problem. And so they provided already a lot of probabilistic tools. And we are going to base our statistical analysis on that. So this is a very nice bridge to give to a very nice move to go to the following slide. That is indeed a slide of recap about some results that are already known in the literature. I move you here. So this is a known result that is actually a combination of the paper I was talking about from Carrillo and al. And other two papers from Catio-Guillan-Marieux and just Marieux. And in this slide, we see really the propagation of chaos. This is exactly what I was explaining before, meaning the fact that if we consider some interacting particle system, they do converge to the independent ones in L2. Like the classical propagation of chaos, it's just what's written here. And in this theorem, the authors went a little bit further in the sense that not only we are considering the convergence from the interacting particle system to the independent one as the number of particles, capital N, goes to infinity, but we also have the convergence of the law of X to the invariant distribution. That is our pi here. How does it happen? Well, it is exponentially time, but you see that if the time horizon capital T goes to infinity, this quantity is going to zero as well. So the nice thing is that we have this quantity nt that it's going to be important in the rest of the paper, and all the results we are going to get will be as a function of nt. That is a quantity that goes to zero as both, sorry, nt will go to infinity as both n and t go to infinity. It's just that the convergence rate of the two of them is different, okay? And this is indeed the propagation of chaos, explaining to us that in L2 the interacting particles are convergent to a dependent one, or in the same way we can also look at the result by really starting from the empirical measure I was talking about before and see that it converges really to the invariant law, which is, as I was saying, a two steps approximation in the sense that the empirical measure converges to the law of the independent particles at a rate 1 over n, and this goes to the invariant distribution at this rate, which is super nice. This is like the propagation of chaos uniform in time that we wanted. It seems perfect, except that we needed something more, meaning the propagation of chaos.
Sorry, for the previous slide, lambda is known, or it is just a constant without any control?
Lambda is this constant that appearing here.
Okay.
And it's
Okay.
and it depends on the constant on the second derivative of both the confinement and
Yes, okay.
interaction potential.
Okay, thank you.
Thank you. That was a nice question. Yes. So okay, this is good. And so it's the classical propagation of chaos in L2. The problem was that for us, L2 is not enough, and we needed something more. We needed a sort of extension of the propagation of chaos in L2P. And the idea was indeed to take exactly the same proof as in the previous paper from Cathiogui and Marieux, and to adapt it. And well, we got lucky and everything worked fine. So it's not so much work to extend the previous one in L2P. The same cannot be said about the second one. And here I'm just like presenting all the probabilistic results before giving the statistical one. And it's not clear yet why we need a propagation of chaos for the Fourier transform as well. But the problem is that we do. So it's not enough to see that the law here of, well, the empirical measure converges to the invariant law. We need to be able to say that if we take the transform, the Fourier transform, but applied in a z that is not real, so actually we get the Laplace transform. Now, I will explain it a bit more in detail. Well, we need to say that the propagation of chaos still holds true. And this is actually a bit more challenging. And well, here I'm hiding some things. First of all, the fact that we'll see later on why we need to introduce this LA, which is...
I have a question.
Yeah, go.
You have a soup in T, and then you say for all T. So I was wondering before seeing that if this thing was really true for the soup over all time, or do you need a fixed time horizon? And this...
It's, well, you take a soup, a fixed time horizon T, but then the constant is, of course, depending on T. And if you don't do anything, the problem is that would be depending on T in an exponential way. You have an exponential of T, and that's bad. But the nice thing is that this constant, well, in this nice result, The constant depends on time, but in a nice way, like it's an exponential of minus something t, so you can bound it by something that does not depend on t.
Okay, so the supremum, it's not over all
Yeah,
small
you're
t.
completely right. It's
Yeah,
between
okay.
0 and capital T.
Okay.
Yeah, you're right. Sorry about
Okay,
that.
thank you.
Thank you. Nice questions. I like you guys. Yeah, you're completely right. So, yeah, indeed, it's the same framework only until capital T, and this constant does not depend on T only because of the nice things, but here the soup is only until capital T. Nice. Okay, going back to the transform. Yeah, here the problem is that later on we will see that it's not enough to consider just the Fourier transform. I don't know if you, again, I don't know how familiar you are with Laplace and Fourier transform, but basically here I gave this, the definition, and if you take a z that is simply a real number, this is exactly the definition of Fourier transform. If you take z that is instead a complex number, this is a Laplace transform. In this sense, we need to generalize the Fourier transform. Why? Because we'll see later on that it's not enough to consider just z that is real. We will need to consider some line that, as explained there, it's a parallel line with respect to the real one. So we will need to understand where are the zeros of some function, and we will say, well, considering only the real line is not enough. What do? Well, I take a parallel one to the real line, where I know that I have not zeros. So I need to be able to move, but it means in particular that Fourier transform is not enough. I need to move to the Laplace transform, and then I actually need to prove this theorem, because otherwise what I'm really hiding is the fact that if Z was real, this result was trivial. It was a consequence of what's called the Kantarovich-Rubinstein theorem. But as Fourier transform is not enough for us, and we need to move to the Laplace transform, this result need to be proven. And actually for us, stuff are a bit more complicated, because using a Laplace transform, for example, not even Plancherel theorem holds true directly. One has to work, okay? I don't know if there are any questions. No?
So
Yeah.
I have a question. So
Yeah.
if, for example, I imagine that the problems comes from the Fourier, from the zeros of the Fourier transform of the interaction potential.
It's actually the Fourier transform of the invariant density associated to the problem. That
Okay.
depends on the interaction function as well.
Okay. So I was thinking that if you assume something else about the interaction potential, some sort of something like positive definite or something like that, maybe you can survive only with Fourier transform. It should be an a priori knowledge on the.
The problem is that it will appear later on that it's really the Fourier transform of this quantity, you see, that it depends on the coefficients, but it's not explicit.
Yeah, okay, I see.
And so still you need to work on that. You need to prove some lower bound on the Fourier transform of this quantity. And really, it's way more challenging. And it's indeed more or less, I mean, we try to do more or less what you said, meaning try to find some assumption on V and WU such that the Fourier transform works well. And we do have some answers at the end, in the point 5. But we will see later on that they are more challenging than expected. That's a good point. Are there some other questions? We go on. We go on to the estimation procedure. It's finally time to propose an estimator. How can we do that? Remember that we want to estimate WU, but it's not easy, and our estimation procedure will consist of 4 different steps. The first step is to estimate what I call L, and it's like the total drift function. This is the drift function dot. And estimating the drift function actually, for classical stochastic differential equation, it's a common problem. Well, there are a lot of papers already. There's a lot of literature. It's nice. one can choose the estimator he wants. And in our case, we decided to consider a kernel density estimator. So, as it is quite common for classical stochastic differential equation, one can consider the drift as well, the derivative of the invariant density divided by the invariant density, and you can estimate each of these two quantities in a separate way. Now, it's true that for us, it's not like having just classical stochastic differential equation. We do have some interaction, but we will see in our result that it does not play a lot of roles. Why? Because the original Brownian motion are independent. One can use the propagation of chaos to move to the actual independent particles, work on the independent particles, and go back. So here the problem, it's really the same as in the classical case, for the classical stochastic differential equation. One introduce kernel density estimator, they depend on some bandwidth. And the bandwidth, H0 and H1, need to be chosen. Here, what I want you to remark is the fact that, in general, when one does nonparametric estimation, there is some assumption about the class where the invariant density or the drift belong. Meaning, generally, one knows what's the smoothness of the drift or of the invariant density. And the order of the kernel is chosen by the statistician as a consequence. Here the idea is the same. We want to choose the order, but we see already that there is a constraint appearing, given by the fact that V may or may not be C infinity. So we can still choose the order of the kernel, nice, but it's important to know that the order of the kernel is always upper bounded by the smoothness of the invariant density that is indeed capital M, okay? So the smoothness on one side helps because you can get like better statistical results, but on the other side, it's a problem because it's more difficult to work with the Fourier transform. So there is this trade-off. Then the second step is about the estimation of alpha, because here we have estimated the total drift, but the total drift is given by V, whose form is known, and the interaction part. And in the V part, well, there is this parameter alpha appearing that may or may not be known. And in this case, we wanted to consider like the more general case where maybe alpha it's not known. And in this case, it has to be pre-estimated. But how can we pre-estimate it? Well, this is something that is again taken from the classical SDE case. One introduces a contrast function and minimizes the contrast function. So it's not so new. So I would say let's go to step 3 and 4, which are really the most challenging part. Because indeed, in 3, what we want to do is to say, okay, we know L. We know all this part about the confinement potential. We can use it to recover an estimator about the convolution. So the interaction function convoluted with the invariant density. And this is what we do. So we get an estimator for this quantity. And this is just like a consequence of the first 2 steps that are very much inspired by what happens in the classical SDE case. So until step 3, one uses the part coming from before. But then we need to be able to isolate the interaction function. So we need to understand how to get just WU. We see why the Fourier transform is appearing. Why? Because if we have an estimate for all the convolution part, well, and we want to isolate just WU, this is a convolution problem for which if we take the Fourier transform of the convolution, this is the Fourier transform of the first times the Fourier transform of the second. And so if you want to isolate this guy, well, you divide by the Fourier transform of the other. This is the idea. So the Fourier transform of the convolution is Fourier transform of the first times the second. So one would like to isolate the Fourier transform of just this guy. But you see that the problem is going to be really that we need to put the Fourier transform of this guy at the denominator, and we need to be able to say that, well, it's not zero. How can we do that? Well, here we use a trick. And the trick is to say, we use the Tikhonov type regularization. So we introduce some extra entire function rho, such that we know that at least on this set LA, the two of them are not zero. Okay? So we are going a bit above zero, so that we can propose the estimator really saying, well, I do take the Fourier transform of what I got in step 3 divided by not only the Fourier transform of the empirical measure, that is our estimator of the invariant density, but plus something more, that is an extra entire function that I really need in order to say that this guy is not zero, so that I can put it on the denominator. That's the idea. Okay.
Sorry, so just
Yes.
one question. If this function rho depends, in fact, on your knowledge about, okay, depends on the assumption of the pi, on the v and w and so on. Yes, it depends on this constant that you mentioned at the beginning of your assumption.
Yeah, it depends on everything, because indeed, yes, the constant appearing already when we are working on the upper and lower bound on the density depends on the same constant as well. And so rho, as a consequence, will depend on the constant on the density and so on, the original constant again. Yes.
Okay, thank you.
Thank you. Yeah, and this is indeed the main problem. The main point is that the analysis of this Laplace transform is crucial in our work. So let's just provide the result and then I'll explain something about the Laplace transform. What's nice is that indeed asking that the tails of the interaction function are exponential, we're able to get polynomial tails for the step 3 so far. So I'm not talking about transform yet. This is just for the estimation of psi that was indeed the convolution between the interaction function and the invariant density. And here we see already some parallelism compared to what we had in the classical deconvolution problem, because as said before, asking exponential decay of the tails, it was possible to obtain polynomial rate for the classical deconvolution problem. But it's just an intuition, because then later on all the proof and everything is different. But it's already nice the fact that we managed to find polynomial rate for the convolution of W first and the invariant density. Here, what's interesting is also the fact that this M is the order of the kernel I was talking about before. And well, the bigger M, the better the rate. So as the order is chosen by the statistician, me as a statistician, I would like to take M as infinity. But maybe I cannot. In the sense that if we are in the second case where we broke the smoothness of the confinement potential, we cannot take M as big. And so in the best case scenario, this is going to be capital M, that is indeed the smoothness of the confinement potential. This is nice, but it's still, well, it's not yet the result we wanted, because we wanted to arrive to something for WU. And in order to obtain polynomial rates for the interaction function, this extra assumption needs to be asked. And here you see it's really close to what you were saying before, like we really want to a condition on the Fourier transform of pi, and we would like to put some condition on the model, on the coefficient, in order to get some nice decay for the Fourier transform. But we need to be careful, because if we put too many conditions on the model, on the coefficients, then also the Fourier transform of WU will change. So really, the crucial point is that the transform of the interaction function and the invariant density need to compensate so that this guy is bounded for some A. So I'm not asking it to be integrable everywhere. I'm just saying that I need one line parallel to the real one line such that on that line, this guy is integrable. Okay? And if it's the case, then I know that this RT looks bad. And well, the important thing to understand is that this RT is just a polynomial rate. Because indeed, okay, up to this logarithmic term, but we don't actually care about it, there is this extra exponential appearing here, and U has to be chosen by the statistician because using a trade-off. But what's important is that this U is basically a square root of log t. And so this exponential is negligible compared to the polynomial 1. And in particular, if the line for which we know that this condition holds true, it's the real line, it means that we can choose A equal to 0. And if A is equal to 0, this guy does not appear at all. But otherwise, in the more general context, we also have this extra guy. And this is the convergence rate appearing in the end, which is something that is, again, depends on all the constant appearing before, and it may seem a bit weird, but what's nice is that it is indeed polynomial. So, but in order to get these things, we really need this condition, which is quite tricky. And we're really asking to have a line parallel to the y-axis such that we have no 0. And this is the reason why we had to replace the Fourier transform with the Laplace one. The nice thing is that, well, okay, it is optimal. I mean, it's not always optimal because you see here that we were able to find a lower bound. And the lower bound, we showed that the convergence rate is n to the power minus 1 over 4. While for us, what was the convergence rate again? Well, it was something weird. It was something weird, but up to logarithmic term, this was the rate. And you see here that in general, our rate, okay, it's polynomial, nice, but it's not exactly the same. True, but I want you to remark something. That is the fact that if we consider just the C infinity case, so we can take M as infinity, well, this gamma is just 1/2. And so our convergence rate is again minus 1/4. And so we recover the optimal rate, but only in the case of C infinity. Otherwise, still an open questions. And then just to conclude, I want to give some idea about the Fourier transform. Why that? Well, because yeah, it's true that everything is nice up to say that this condition all true. But I don't want you just to like have faith in me, trust me when I say that it's possible to obtain pi and WU actually satisfying this condition. I want to give you an intuition about how the fact that we have less smoothness helps us in getting the nice decay for the Fourier transform of the invariant density. So I give you just a bit of intuition. How can we do that? Well, in order to do that, we need to consider the zeros of the Fourier transform of our invariant density and study the order and the critical exponent. Now, without going too much into detail, what's nice is the fact that using Hadamard representation, we are able to show under very nice hypothesis, that is just the fact that the critical exponent is smaller than this guy. Then the Fourier transform behave, well, it's lower bounded by the exponential of minus z squared outside the ball where we do have the zeros, of course, otherwise it's just 0. But that is nice because remember that we wanted to prove these things, and sometimes well, we can get that also the Fourier transform of W first compensate this guy. How? Well, it's enough to have this condition that holds true on the Fourier transform of WU. Are we asking a lot? not really. An example is the fact is when we consider linear combination of Hermite function. And in this case, you see that we have like exponential of minus z squared, both a numerator and denominator. And so actually this condition all true under very mild condition. But this lower bound on the invariant density, well, it's not optimal in the sense that sometimes it's possible to do more. How? Well, if one knows that the confinement potential has some smoothness that is not C infinity, but has a certain smoothness that is fixed and you cannot go behind that, well, then it's easier because you can construct, you can show physically that the Fourier transform is lower bounded by something that is even polynomial. And here it's just the example to make you understand. If we consider W, and V that are okay, infinitely differentiable on R, but V has a discontinuity point in 0. I mean, the M derivative. The M plus 1 derivative has a discontinuity in 0. Then what's nice is that also the invariant density, whose form is completely known, has a, well, the derivative has a discontinuity in 0. And why is this useful? Well, because we can write the Fourier transform of pi integrating by part and making appear all the derivatives. So we can go on and on up to the M plus 1 derivative. And each time we get a z denominator. This is given by the fact that when you derive, you are just like multiplying by z. So if you integrate by part, the z goes at denominator. And then this true quantity, I minus and I plus, are explicit, and they can be studied in detail. And here I wrote just I plus, but for I minus, it's exactly the same. This quantity, I plus, is given by integrating by part once again, what happened in 0 plus, minus something else, which is actually negligible compared to this guy because of Riemann's lemma. And so putting the things together, we are saying that with I plus, we get another power of z. But so, I put you here, but so it means that we really have a development for the Fourier transform of pi, and in this case we get that the lower bound is even better, it's polynomial. So what we had before using the Hadamard representation was just like one example for having like in general a way of obtaining that the assumption on the Fourier transform is respected, but sometimes it's possible to do better. How that? Using the fact that we broke the smoothness of the confinement potential. So just put everything together, and then that's it. If we put everything together, the take-home message is that, first of all, we have seen together some probabilistic results we needed in order to get our statistical result. And I wrote them here as finally they may have an interest by their own. And these two results are the propagation of chaos in L2P and the propagation of chaos for the Fourier transform of the invariant density. After that, we started with the statistical procedure, and we have actually found that if the interaction function has exponential tails, then we do have polynomial convergence rates for the estimation of this object, where the deconvolution problems start appearing. And indeed, in the following part, we want to isolate the interaction function, and we did isolate it, but adding another assumption on the joint decay of the transform of these two guys. Under that condition, it was actually possible to get polynomial rates, and we have proven that, at least in the C infinity case, such rates are optimal. In the not C infinity case, I don't think so, but it's still an open question, so it's just my intuition. And then to conclude, we have seen that employing some tools from complex analysis, it's possible to find some examples where this condition on the joint decay actually holds true. So it's not like we are asking something too crazy, let's say. And that is all. By showing you the references, the reference about this talk, I concluded. Thank you very much. I don't know if stopping to share the screen also, or maybe not, because if there are questions, maybe you will need them before. I don't know. You'll need them.
Perhaps a question about the optimality. So in the NT you used, there was a dependence in N and in T. So is your optimality valid in both directions?
Yes, because everywhere, like all our convergence rates are function of NT. So we really take like NT. We never split how it happens in N or in T.
Okay, but in the lower bound, what appears is NT or it's just N? I don't remember.
It's NT as well.
It's NT as well. Okay, so
if it doesn't, it's a typo, but it's sorry about it. You are completely right again. Haha. It's really nice working with you guys. Yeah, no, it should be.
Okay, so okay, thank you.
Thank you. Some other questions?
So can I ask some question?
Sure, I'd love to.
I would like to know from the original problem is you fix some time t and you say that you have some you observe what happens at time t, but can you improve this inference if you observe all the paths until time t? Okay, not all the paths, but some times before time t.
Yeah, you mean what happens if maybe you can really have all the trajectories starting, even like in the best case scenario, having all the trajectories starting from 0 to t, if that would improve our analysis. Is that the question?
Yeah, yes, it is a question. Of course, you cannot have all the paths. You can add also sometimes.
Even some discretized, like in high frequency or whatever. Actually, it's a very good point, because what happens is that there is a nice work from Richard Nicol, Greg Pavliotis, and Colin Ray on the annals, and it appeared really, I don't know, like this year, I would say. And what happens is that they consider a similar problem, but it's a bit different. So, okay, let's answer to your question first, which is in considering what we have done, it doesn't help having something else that is really close to, well, some other extra observation before time t. Doesn't help really, because anyway we are going to consider just the ergodic case, so we really need to wait a lot of time until time capital T goes to infinity. So even having some extra assumption before, we would lose them, and so that wouldn't help. But on the other side, talking with them, what we discovered is that it would be different if instead we do not give enough time to the solution to actually become smooth. In the sense that what they do is to start with something that is not smooth. They give like an initial condition that is not smooth, and they see what happened very close to the initial condition. And of course, it's a different type of work, because you don't talk about like ergodicity and so on. But in that case, indeed, it's possible to like obtain some polynomial convergence rate again. And it's nice, the idea that really, if you stick close to the initial condition that it's not smooth, you can again work with very nice decay for the Fourier transform, and you don't have the deconvolution problem. Which, if you think about it, it's weird, because like from a statistical point of view, it's nice to have smooth things, right? So it seems that like starting with something that is not smooth should complicate stuff. But I mean, for me at least, my understanding is that maybe it's because the deconvolution problem is like more complicated than the statistical problem, or at least the statistical problem is already well understood because we have a lot of references, while in this context, the deconvolution problem is a bit more new. I don't know.
Okay, thank you. I have some other question. So here,
Yes.
if I understood it, everything is in dimension 1, yes?
Yes.
Yes. So, and okay, I don't know if you know of this field of active matter physics, which is close to biological systems, in which there are some kind of McKean-Vlasov equations, but you have two variables. For example, you have the position of the particle, but you have also the angle of the velocity. So in this case, it is a bit more complicated. I don't know if
That's a very
you
good
thought
point.
about
That's
this.
a very, very good point. Indeed, I think that if we go back to the statistical procedure, I feel that, well, for the probabilistic point of view, the probabilistic tools are not a problem in higher dimension. And when we consider like the first two steps, I feel like there aren't any problem either, in the sense that if you want to estimate just the drift, you can do it in a higher dimension. There's even this very nice paper from Mark Hoffman and Letizia Della Maestra where they do consider like drift estimation in dimension D, and everything is nice. If you want to move until step 3, I think that there aren't many problems, but I wouldn't know how to arrive to at the final step, like really considering the deconvolution problem and also studying the Fourier transform of the pi. Maybe in some particular cases, if we can somehow factorize what's happening in the different components, maybe it's possible, but in general, it seems really messy. But on the other side, last thing, what you said about the fact that it's nice also the fact that like one stochastic differential equation is for the position and the other is for the speed. The other difference is that in one of them, like sigma is equal to 0. So you should also be able to consider the case where like sigma, or by sigma I mean the diffusion may be degenerate. And that I don't think is really a problem. So here the problem is really due to the fact that moving to higher dimension has a problem from the deconvolution point of view.
Okay, thank you.
Thank you. It's interesting indeed, but so far it's a bit challenging.
Maybe I can ask, are there many other questions or comments? If that is the case, then let's thank the speaker.
Thank you.
And thank you for the very nice talk.
Thank you again.